Within an industrial facility, there may be hundreds of different fluid systems designed to control and direct fluids for a variety of operations. Each system is made up of a series of valves, piping, pumps, and other components. Fluid system components are susceptible to leaks. Two common devices used to prevent or minimize leaks are gaskets and packing. Gaskets are commonly used to seal non-moving connecting surfaces, such as pipe flange faces or the two halves of a pump casing. Gaskets are made of compressible materials that can be squeezed. When a gasket is squeezed between two connecting surfaces or sealing surfaces, the compressibility of the material allows the gasket to form a seal. This illustration shows a gasket between two sections of pipe. The gasket is installed between the smooth sealing surfaces or faces on the connecting flanges at the end of each pipe section. As the flanges are bolted together, the gasket is compressed or squeezed between the faces. As the bolts are tightened, the gasket material is forced into any small imperfections in the sealing surfaces of each flange. As a result, leakage paths are blocked off. Gaskets are made of compressible materials that can be squeezed. When a gasket is squeezed between two connecting surfaces or sealing surfaces, the compressibility of the material allows the gasket to form a seal. This illustration shows a gasket between two sections of pipe. The gasket is installed between the smooth sealing surfaces or faces on the connecting flanges at the end of each pipe section. As the flanges are bolted together, the gasket is compressed or squeezed between the faces. As the bolts are tightened, the gasket material is forced into any small imperfections in the sealing surfaces of each flange. As a result, leakage paths are blocked off. This exaggerated illustration represents a flange with large imperfections in the sealing surfaces, such as deep scratches. A gasket may not be able to fill these deeper imperfections. As a result, leaks might occur. The surfaces should be polished with grit paper or machined to remove the imperfections. This illustration, enhanced to show detail, represents a flange with a high spot. This type of problem may not allow a gasket to compress evenly, creating a leakage path. The surface should be machined to remove the high spot. A cracked flange, exaggerated here to show detail, could also prevent a gasket from sealing properly. If the crack is deep, it may be impossible to repair, and the flange may have to be replaced. If the flanges are out of alignment or the sealing surfaces are not evenly machined, the sealing surfaces may not be parallel. If the sealing surfaces are not parallel, the gasket material may not compress properly when the flanges are connected. One way to determine whether the sealing surfaces are parallel is to measure the gap between the opposing flanges at several points around the flange. If all the measurements are equal, then the sealing surfaces are parallel. Gaskets can be made from many different types of material. Some common materials include metal, Teflon, cork, paper, and rubber. Each type of gasket material is designed for a specific range of applications. Matching a gasket material to an application depends on a variety of factors, including fluid temperature, fluid pressure, and the material's compatibility with the fluids in the system. Though you may not be responsible for choosing a gasket material, you should be able to verify that you have the correct material for a specific application. One way to verify that you have the correct gasket material is to check your company's maintenance procedures. If you're working on a specific piece of equipment, you may be able to consult the equipment manufacturer's manual to determine what gasket material should be used. A more comprehensive source of information can be obtained by consulting a physical properties chart. This type of chart, provided by most gasket manufacturers, rates the physical properties of common gasket materials. Each material is rated according to a list of criteria that indicates how the material will react under certain conditions. The information can help you determine the full range of applications for which a gasket material can be used. There are essentially two basic types of gaskets, flat gaskets and O-rings. Flat gaskets are typically thin, wafer-like devices designed to cover all or much of a sealing surface. Flat gaskets can be pre-formed by a manufacturer, or they can be cut from a sheet of gasket material. Flat gaskets come in many varieties to suit many specific applications. For example, the casing for this low-pressure cold water pump is sealed with a flat paper gasket. This economical gasket has a low pressure rating and is not suited to high temperature situations. It's well matched to this low temperature, low pressure application. The other basic type of gasket is an O-ring. Most O-rings are made from rubber or Teflon and are preformed by the manufacturer. Some O-rings are made using material that must be cut to length and glued together. Unlike a flat gasket, an O-ring is not simply sandwiched between two flat sealing surfaces. Instead, the O-ring is seated on one of the sealing surfaces, typically in a shallow groove. When the opposing surfaces are bolted together, the O-ring is compressed slightly within the groove, seating it firmly in place. This is only one example for seating an O-ring on a flange. There are many other flange variations, but one thing they generally have in common is a special fit that helps hold the O-ring in position when it's compressed. Fluid system components require regular maintenance. Because strong seals are vital to the integrity of a fluid system, gaskets are often replaced as part of any regular maintenance routine, whether they show signs of failure or not. Though many flat gaskets come in preformed shapes and sizes, some common replacement applications call for gaskets that are cut from sheets of gasket material. If the application calls for a circular flat gasket, one way to create the gasket is to use a gasket cutter. This gasket cutter consists of a cutting board with a small hole in the middle, a pin that fits into the hole, and a cutting tool. The cutting tool fits over the pin and has an adjustable blade for cutting the inside and outside diameters of different size gaskets. Let's watch a mechanic use this gasket cutter to cut a circular gasket to fit a pipe flange. Before he begins, the mechanic verifies that he has the correct gasket material by checking his company's maintenance procedure. To prepare for cutting the gasket, the mechanic measures the inside diameter of the flange and the outside diameter of the flange. These measurements will allow him to set the blade on the cutter to cut a gasket that will fit the flange exactly. Next, the mechanic sets up the gasket cutter. He pushes the pin through the gasket material, then places the pin in the hole on the cutting board. The mechanic then positions the cutting blade using the outside diameter measurement so that it will cut the outside edge of the gasket. The outside edge should always be cut first. The mechanic places the cutting tool on the pin and begins the cut by rotating the cutting tool. Once this cut has been made, the pin will still hold the gasket material in place so that the inside edge can be cut. When the cutting tool completes a full circle, the outside edge of the gasket has been cut. The mechanic then removes the cutting tool from the pin and readjusts the blade to the inside diameter measurement of the pipe flange. He places the cutting tool back on the pin and turns it one complete circle to cut the inside edge of the gasket. When the cut is complete, the mechanic removes the tool from the pin. If required, bolt holes are punched through the gasket using a hole punch and a hammer. Once the gasket has been inspected for tears and rough edges, it's ready to be installed. Not all gaskets are circular. In fact, some gaskets form very irregular shapes. Irregular shaped gaskets are typically cut by hand. For example, this low-pressure pump requires two irregular shaped gaskets. Let's see how the mechanic cuts a gasket to fit this pump. First, the mechanic must verify that he has the correct gasket material. He refers to the pump manufacturer's manual for information about the gasket material that should be used. After the mechanic obtains the correct gasket material, he must accurately cut a gasket to fit the shape of the sealing surfaces. In order to do this, he must transfer the shape of the sealing surfaces to the gasket material. This can be accomplished by coating one of the sealing surfaces with a substance that will transfer easily to the gasket material. In this example, the mechanic coats the sealing surface of the upper half of the pump casing with a type of dye called bluing. After the mechanic obtains the correct gasket material, he must accurately cut a gasket to fit the shape of the sealing surfaces. In order to do this, he must transfer the shape of the sealing surfaces to the gasket material. This can be accomplished by coating one of the sealing surfaces with a substance that will transfer easily to the gasket material. In this example, the mechanic coats the sealing surface of the upper half of the pump casing with a type of dye called bluing. The mechanic places the upper half of the casing onto the gasket material and presses down firmly. As he carefully removes the casing, some of the bluing transfers to the gasket material, creating a pattern. The mechanic uses snips to cut the gasket material, following the pattern. Snips are a good tool to use for this procedure, since they can easily cut along the irregular edge of the pattern. When he's finished cutting the gasket to the desired shape, the mechanic uses a hole punch to make bolt holes in the gasket. A hole punch is the best tool for this step because it cuts a clean, precise hole. Well-formed bolt holes are important because they allow connecting bolts to thread easily through the gasket material to avoid tearing or buckling. The mechanic places the gasket on a piece of wood and positions the hole punch over one of the hole shapes on the pattern. He then strikes the punch with a hammer to make the hole. The process is repeated for each bolt hole in the pattern. Once all the bolt holes have been punched out, the gasket is ready for installation. The mechanic then cuts the other gasket for this pump following the same procedure. We've seen two ways that gaskets can be cut. Now try a question on cutting gaskets. In this part, we'll look at how gaskets can be installed. We'll view the installation of a gasket on a pump casing, and we'll see how an O-ring can be installed. Let's start by following a mechanic as he installs a two-piece gasket on a pump. This pump was properly tagged and locked out according to company maintenance procedures. The pump has been drained and vented to remove system fluid. The mechanic needs to install a new gasket between the two halves of the pump casing. This application requires a two-piece gasket made to fit each side of the casing. First, the mechanic must remove the old gaskets. He uses a scraper to remove the old gasket material. As he removes the old gasket, he's careful not to damage the sealing surfaces. When the old gasket material is completely removed, the mechanic disposes of the old material according to company procedure. He then inspects the sealing surfaces for signs of damage. If there are any scrapes or gouges on the sealing surfaces, they must be repaired before the new gasket is installed. Small imperfections may be removed by polishing the surfaces with grit paper. Larger imperfections may require that the sealing surfaces be machined. The sealing surfaces on this pump appear to be in good shape, so the mechanic can install the new gaskets. When installing new gaskets, the equipment manual for this pump recommends using gasket compound on the sealing surfaces. There are basically two different types of gasket compound. They are hardening and non-hardening compounds. Hardening compounds generally dry to a hard finish and often act as an adhesive to hold a gasket in place on a flange. Non-hardening compounds remain soft or tacky. They can function as a sealant to help fill in imperfections on a sealing surface. The manual for this pump recommends using an anti-seize compound. After removing the bluing substance from the casing, the mechanic applies the anti-seize compound to the sealing surface. He applies the compound to the lower half of the pump casing as well. The mechanic then places the gasket halves on the sealing surfaces of the lower half of the casing. He carefully lines up the gaskets with the edge of the pump casing and checks to make sure that all the bolt holes in the gaskets are properly aligned with the bolt holes in the casing. If the bolt holes don't line up perfectly, the holes can be punched again to slightly enlarge them. Forcing bolts through holes that are incorrectly positioned could cause the gasket material to tear, and the gasket might fail as a result. If a gasket is torn during installation, it should be replaced. Once the gasket is properly in place, the mechanic installs the upper half of the pump casing. As he does this, he is careful not to damage the gasket. After the upper half of the pump casing is in place, the mechanic prepares to install the bolts that hold the casing together. He first cleans the bolts